This week, I want to talk about image preprocessing, which is really the first step in the processing pipeline that we're going to go through when we analyze our fMRI data. And I'm going to do it in 4 relatively short videos this week with the aim of motivating image preprocessing. I mean, why do we do this in the first place? Why don't we just jump right into the statistics? And as part of that, I want to explain why we delete dummy volumes. I want to describe in some detail the realignment process, which is often referred to as motion correction. And part of that description, I want to explain why I don't like the term motion correction. And finally, in the last video, I'm going to discuss slice timing corrections and also whether or not we actually need to use them. Okay. So in this first video, I really want to focus on something that are often referred to as dummy volumes, but I've referenced earlier in the module when I've talked about T1 longitudinal relaxation effects. And this is something that came up when I was talking about sparse sampling. And I said that this is an issue that we would come back to. Now is when we're coming back to it. So the first thing I want to do, though, is start with why do we do this pre-processing at all? Why don't we just simply take the data that we've collected and go ahead and do our statistics? And the reason for this is that there are various sources of noise in the data that we can correct for, and there are various sources of noise that we're going to actually try to model with our statistics. And some, you're going to apply the right tool to the right source of noise. So there are non-task related sources of variability. That is, things that are going on that have nothing to do with your particular experiment. And those are the things that we're going to try to address in pre-processing, which means that we don't need to know what the experiment was, how it was conducted in order to do the image pre-processing. That's going to be an important characteristic, because if you do need to know that, then you're getting into the area where you're doing pre-processing in order to enhance your results in a way where you start to fish, right? You're actually doing what we call fishing, which is adjusting your data to try to fit your hypotheses, which is not a valid thing to be doing, okay? And the purpose of the pre-processing will be to remove these sources of variance rather than try to model them, for instance. And I'll talk about that distinction. And as I said, this is all done without having any reference to the experimental design. There is one exception that I'll talk about post hoc here. Okay, well, what are some of these sources of non-task related variability? The first one that I want to talk about, particularly in this video, are these T1 longitudinal effects, which I'll explain in a second, but also head movement. So that is to say, as long as you're alive, you are moving your head, and as hard as you try to stay still, there are still head movements that affect our data collection, and I'll talk about why in the following videos. And then finally, I want to talk about the slice timing issue, right? So I raised this when we talked about avoiding bias in designing experiments. And this has to do with the fact that you don't collect the whole brain data all at the same time. It happens over, over a period of time, the repetition time in particular. And that has implications for the way we actually sample the data. And we'll talk about that in the final video this week. One of the other things that is going to be important, but I'm not going to talk about this week, it'll be next week's topic, is that there are differences in things like people's head size, and therefore the size of their brain, and the shape of their brain, and its position, whether your head is sort of perfectly placed in the scanner, whether it's a little bit off to the side, you're angled funny. All of those things are sources of variance that we're going to need to address. Okay, so let's talk about what are often referred to as dummy volumes or T1 longitudinal effects. So this is actual EPI data, so that is echoplanar imaging, fMRI data, from a study that I collected in Oxford years ago on a 3T scanner. And you can see that you got 3 planes here. You've got your sagittal plane, your coronal plane, and your axial plane in order from left to right. And you can see that fMRI data tends to look like a bit of a ghost brain. It's not beautiful, it's a little bit chunky, and there's a lot of variance in the brightness. But I have this on a little repeating video loop, and hopefully what you can see is I only have the first 10 volumes playing here, and it's just, as I say, repeating. You can see these bright images that actually start at the beginning of the time series. So if I bring it back, it starts bright, and then it gets less bright, and then it sort of calms down. And I'll let that loop as I discuss it. But these are the T1 longitudinal effects. That is to say that the initial images that you collect when you turn the gradient coils on are significantly brighter than subsequent images. And there's a really quick tail off on these kind of things. And the problem is that that initial brightness is an order of magnitude or more larger than bold signal effects. So there's an artifact in these data that needs to be removed. The easiest way to do it is simply to delete the first couple of volumes, and we'll talk about what the number of volumes should be. The size of this effect depends very strongly on the field strength of the magnet. So 1.5 Tesla magnet, such as the one we have downstairs in Buckney, will give smaller T1 longitudinal effects than a 3T magnet and much smaller than a 7T magnet. Okay. So if we just move on, let's move on. Come on, slides. There we go. This is a slide that I showed you before, and I just want to return to it just to sort of illustrate where the effect comes. As we said, that the MRI scanner is working on the fact that hydrogen nuclei, that is protons, are spinning and therefore act as little magnets. So when you put them inside the magnetic field, they tend to align with the magnetic field, and you have a net magnetization, which is shown here as MZ, right? Because all of those very, very, very tiny magnets are lined up in the same direction, there is an increase in the magnetic field in that direction. That's the net magnetization. When you do EPI and you put in a radio frequency pulse, you actually push those things over about 90 degrees. So rather than being sort of upright with the magnetic field, they now flatten out and they're in this plane. And as a result, there is no net magnetization running in this sort of Z direction anymore, right? And then they relax, and you can see that that increases over time. If I were to just sort of plot this, what happens is that RF pulse knocks the net magnetization down to 0, which is the starting point, and then it relaxes in this exponential growth curve, right? And the time it takes to reach that steady state is called the T1 constant, the first time constant, or the longitudinal time constant. That's what T1 is. However, before it reaches magnetic equilibrium, a second TR pulse comes in and knocks it back down to 0. Okay, so what happens here is that you can see that initially, by the time that second TR RF pulse comes in and knocks things down to 0, it hasn't reached steady state yet. And in fact, in the one after that, it hasn't reached steady state yet either. So what you get is that after a set of these volumes, the TR pulse, as long as it's coming at a regular interval, every 3 seconds, every 2 seconds, whatever, is going to produce the same increase in relaxation and then decrease down to 0. That is the kind of steady state where all of a sudden we don't have these brightness effects anymore. Because in those first two volumes, you can see that the signal is relaxed to a larger extent. You actually have more brightness in the image. So this is what I've modeled on a 1.5 Tesla machine. Typically on a 3 Tesla machine, you would delete more than 2 volumes. But it depends a little bit on the TR as well. So longer TR means that you delete fewer volumes because you're closer to the actual T1 longitudinal relaxation. On a 7T scanner, you probably delete quite considerably more volumes than this. But the key is that those initial volumes are always going to be contaminated by these longitudinal effects, which means that when you plan your experiment, you want to make sure that you don't start your experiment when the scanner starts, because otherwise you're throwing out data that are potentially valuable. You want to let the scanner start, collect its steady state, enough volumes to reach steady state, and then start your experimental paradigm so that you're not throwing out data that's of interest to you as well. You're only throwing out dummy scans.